I'm Bailey Thomas, and alongside me is Justin Bohr, and today we're going to be debating the serious debate. The serious debate is a glacial geological controversy that is about how old glacial deposits are that were found near Mount Sirius in Antarctica. From offshore drilling, scientists have determined that the processes of glaciation started occurring in Antarctica roughly 34 million years ago, and potentially even prior to that. The records of the glaciers come from the Transantarctic mountain range and also come from the Prince Charles mountain range. Scientists are concerned with the Transantarctic mountain range because it is unclear how old the rock deposits found there really are. The glacial deposits left behind from the Transantarctic mountain range are very important because it helps us understand past ice sheet stability. Past ice sheet stability is very important knowledge to have because if we understand the past and what has happened to the ice sheets, then we will know what will happen in the future. The only type of rock that matters to researchers about the serious debate are a dimicetite, or a crudely arranged sediment that comes with a large amount of variance in stone dimension and form. Scientists have looked at comprehensive reports on the rocks in laboratories and concluded that the rocks formed had to be from glaciers. But they were formed from glaciers under a different environment that was much hotter than today. On top of that, the rocks are connected to mats of vegetation. These areas of vegetation are very similar to those found in New Zealand, Tasmania, and also Patagonia. This has led scientists and researchers to believe that the average annual temperature for forming these glacial deposits are around -5 degrees Celsius, which is approximately 25 degrees Celsius warmer than today. In this serious debate, there are two parties, the stabilists and the dynamicists. The stabilist position is that the rocks are much older and that the ice sheet has remained constant the past 34 million years. I will be holding the dynamicist position that the rocks are much newer age and belong to the Pliocene epoch. Good.
Hi, I'm Justin Bohr. I'd like to begin by discussing the importance of the polar ice sheet. The polar ice sheet has existed for at least 14 million years. It is approximately 3,000 to 4,500 kilometers long and covers the area of Antarctica from coast to coast. It is important because it acts as a global heat sink and regulates temperatures worldwide. It also influences the ocean circulation and determines the global sea level. Marine sediment cores have provided evidence to suggest that the present Antarctic ice sheet developed over the last 40 million years. Due to Australia moving away from Antarctica and the Drake Passage opening up between the Antarctic Peninsula and South America, the ocean and atmospheric circulation created the conditions necessary for glaciation roughly 40 million years ago. The origin of this stepped growth view and the glacial conditions that led to more glacial growth is that it is resistant to change, aside from major environmental changes. The main geological change during the Pliocene was a thickening of outlet glaciers. This is based on a geomorphic study of the landscape. There is little evidence that there has been much modification from glaciers, i.e. melting, apart from scouring of lower plateaus and valley deepening. This idea is supported by dates on a variety of landforms which lean towards the conclusion that the landscape has been stable for approximately 14 million years. Using volcanic ash to date the superficial till sheets, old desert pavements, and avalanche deposits on slopes of 30 degrees, it was discovered that these areas span the Miocene and Pliocene. Because these features are considered fragile, the fact they have survived so long and not succumbed to erosion is another clue to the stability of the ice sheet. The Sirius group deposits are located on high-altitude plateau remnants that predate landscape dissection, and if the dissection was finished during then the Sirius group deposits are much older.
Okay. I believe that the rocks found are much younger than what the stabilists make them out to be, and also that the ice sheet was warm. The rocks derived from the Pliocene epoch about 3 million years ago. In this time frame, Earth was much warmer, and dynamicists have found, through dating the ages of diatoms, or very small sea life organisms, that they are from the Pliocene epoch. The Pliocene epoch had warmer conditions that would be similar to ours today because of global warming. It is predicted that within the progression of global warming, by the end of this century, sea levels will be similar to those in the Pliocene epoch. I believe that the East Antarctic ice sheet was diminished a huge amount, and this prompted gargantuan sea levels to occur. This makes sense because of our sea levels rising large amounts today, and as we progress towards the end of this century, it will only climb. The diatoms found are thought to be from marine passages in the interior of East Antarctica. For this to happen, an ice sheet must have been structured over time during the Pliocene epoch, and then the ice sheet drifted over to the Trans-Antarctic mountain range. After the ice sheet was there, then the diatoms were deposited into Mount Sirius. The reason why I hold the dynamicist viewpoint is because of how the deposits happened. Dissimilar to cold-based ice sheet deposits, these deposits were a few meters thick. Cold-based ice sheets would have produced a much thinner and smaller deposit. This type of deposit has been found all throughout the Sirius and Trans-Antarctic mountain range. The way the deposits are found gives us a healthy amount of evidence to say that it was a warm-based ice sheet. For additional supporting evidence, geologists have looked at ice drilling holes near the Antarctic continental margin. They've also seen studies from seismic stratigraphic that have looked at the Pliocene warming occurrence, and all of the data remains stable and consistent in the sense that it provides for a warm-based ice sheet in the Pliocene epoch.
According to an article written by Sugden, Denton, and Marchant, there is also indirect evidence that conflicts with the hypothesis of Pliocene. The preservation of fragile, unlithified deposits on the slopes as steep as 30 degrees implies that no running water can have affected them since depositation. In the case of the avalanche cone in Arena Valley, this covers the last 11.3 million years. In the dry valley today, water action only occurs at low altitudes and leaves fans at the bottoms of slopes. Due to these fans not being present at higher altitudes, it can be surmised that the climate could not have been warmer than 3 degrees Celsius above the present temperature since the Miocene. There has also been buried glacier ice that has been found to have an age in excess of 8 million years. Had there been soil development and vegetation cover, it would have not been found. The temperature would have also had to rise about 17 degrees Celsius to create significant deglaciation. The critical unknown regarding the diatoms is how did they get there? One theory is that they could have been airborne, as they are today, and could have accumulated that way. If this is the case, then the age range of these diatoms could further support the argument of stability. Research conducted by Bruno et al. In 1996 dated the Sirius group Tillites in the Antarctic dry valleys with cosmogenic helium and neon, the noble gases, and came to the conclusion that the ice sheet has been stable since the Middle Miocene. Research using cosmogenic neon in 1999 provided similar findings. Some are feel at all. Denudation rates in the dry valleys are the lowest of any terrestrial environment. Because these rates of geomorphic activity are so slow, it is only natural that their conclusion was that there had been minimal modification of the landscape in the dry valleys area in the past 15 million years. They also used the volcanic ash deposits that dated back to the mid-Miocene. All this evidence points to the hypothesis that the East Antarctic ice sheet has been substantially stable for the past 15 million years.
Thanks for watching.